I'm DilipBalachandran and welcome to the detailed presentation of my project, Twitter Tweets Count by Time Zone. The project involved parsing live streams of tweet samples from Twitter using Apache Flink and counting the number of tweets occurring in a specified time interval, also referred to as tumbling block window. Elasticsearch was used to index and store the documents, whereas Kibana was used to visualize the data. The code for this project was written using Scala in IntelliJ IDE and packaged using Maven. Apache Flink is an open source platform for distributed stream and batch data processing. At its core is a streaming data flow engine that provides data distribution, communication, and fault tolerance for distributed computations over data streams. Flink includes several APIs for creating applications that use the Flink engine as shown below in the diagram. The API supports Java and Scala and more recently Python. The Flink features are high performance and low latency, support for event time and out-of-order events, stateful computation, fault tolerance and lightweight distributed snapshots, flexible streaming windows, batch and streaming in one system, where Flink is more of a pipelined engine rather than a batch engine, broad integration with open source data processing systems such as Yarn, HDFS, Kafka, etc. The data flow used by the application is shown below. Flink connects to Twitter to receive streams of tweets as JSON strings. Each JSON string is parsed for time zone, and counts of time zone for the specified time window are calculated. At the end of the time window, the application connects to Elasticsearch and streams the records to the specified index. The index key for each of the records in Elasticsearch is obtained by concatenating the epoch time in milliseconds. The records are stored in Elasticsearch for consumption by Kibana. So prior to commencing coding, the following activities would need to be completed. Flink would have to be installed and the cluster would have to be started. Prior to starting the cluster parameters would need to be set in the configuration file. We would have to install Elasticsearch, which is as simple as downloading the tar file and extracting it. Once again, there would be configuration parameters involved, which could be found in the elasticsearch.yml file in the conf folder. Once Elasticsearch has been installed and configured, one would have to define the index for the application and the mapping that would be received in the strings from the source application. Third would be installing Kibana, which is very similar to installing Elasticsearch. The tar file would have to be unzipped and it would be ready to go. The only parameter to configure here would be the Elasticsearch URL, which tells Kibana where to talk to Elasticsearch. The fourth step would be to create a projector using Maven. And fifth would be to import this project into IntelliJ for development. The Flink engine provides a dashboard, which is a web front end, and it has a lot of potential in terms of understanding the various nitty-gritties within the engine, monitoring running jobs, understanding the mapping structure of jobs, etc. In order to interact with Elasticsearch, one would have to use RESTful API calls with JSON over HTTP. The diagram or the snapshot below is an example of how to query the Elasticsearch engine for all the indexes that exist. As we can see, there is an index by the name .kibana and the other index, which is twit index, belonging to the application that was written for this project. The third would be Kibana. Kibana connects to Elasticsearch based on the configuration in the parameter file. It discovers index in the Elasticsearch, and the following snapshot shows the dashboard that was made to display all the data accumulated by Elasticsearch from the tweet application. Kibana provides various different visualization tools that can be put together to form a dashboard, and data can be visualized in any which way possible. The application that was written reads a properties file, application.conf.properties on startup, to read authentication and configuration information. This file also has parameters related to Elasticsearch. For example, the Flink _window_time defines the time window in seconds for collecting tweets used in the tumbling block window calculations. If Flink _raw_tweet_log is true, then logging for all the raw tweets is enabled, and same goes for parsed tweets. We can also see that there is Twitter token secret, consumer secret token, and consumer keys, which would have to be passed to the application in order for the application to connect to Twitter. The screenshot below shows a typical JSON string file that is received in every data stream, and the highlighted yellow circle shows the time zone parameter that is parsed from the Twitter file, from the Twitter string. The crux of the code is shown below. We define a data stream that adds Twitter source as its source for data streams. The incoming data stream is processed using a similar approach such as MapReduce and is processed using the tumbling processing time windows function of Flink to collect tweets defined in the window time parameter. The sum of all the tweets belonging to a particular time zone are once again mapped and split into three parameters, which would be the time zone, the number of tweet counts belong to the time zone, and the current time in milliseconds corresponding to epoch time. Following that, the data stream is passed over to the Elasticsearch, whereby the parameters for Elasticsearch are read from the properties file on startup. We now move on to the application demo. To install Flink, one would have to download the TGZ file and extract it. Upon extraction, we can notice that there is a bin folder and a conf directory. In the conf directory, there are various configuration files, and an important configuration file is the flink-conf.yaml. We can edit the Flink configuration by editing the flink-conf.yaml file, which contains various parameters corresponding to the Flink engine. Some of the parameters that we edited were the task manage heap size, the number of task slots for each task manager, and parallelism was set from 1 to 3. Once the configuration is completed, one can go into the bin directory and start the cluster using the start cluster command, and can add more task managers using the task manager command. In this case, our cluster is already started, and how do we verify that the cluster is already started? We go onto the web UI dashboard. The following shows that there are 2 task managers configured for this Flink cluster and a total of 6 task slots available, 3 for each. Below are the completed jobs. One of the jobs ran for 2 days, after which it was stopped. Another ran for 3 minutes, and detailed logging can be viewed by clicking on the link. The following shows the different sections of the code itself: mapping, filtering, the tumbling processing window, and the amount of data that was processed during that time frame. In this case, 31.1 GB over a time frame of 2 days. The Elasticsearch engine, you would have to unzip and go into the bin directory and simply start the Elasticsearch. Once Elasticsearch has been started, we can query Elasticsearch using REST API calls. Below is an example of us querying the indices available in our Elasticsearch. The second thing we need to do is to configure the Elasticsearch's index that the application will be communicating to. In our case, twit-idx was already created prior to starting this presentation. Hence, I will show you what the mapping structure of this index looks like. Please note that details on how to configure this index have been provided in the report. As we can see, the mapping is called zone tweets and expects 3 parameters. First one is the number of tweets, which is an integer, the time frame, which is during which the tweet was collected, and the zone name belonging to the zone in the tweet. Once these 3 have been verified, we can now move on to starting Kibana. Kibana is similarly started by extracting the tar file and starting the Kibana engine from the bin directory. Once Kibana is running, we can access Kibana by going to the URL. The URL for Kibana is available at port 5601, and the following shows the settings for twit-idx, which was already configured. Please note the details for configuring Kibana for twit-idx is available in the project report. The following shows the mapping that is also present in the project report. We will now move on to discussing the code. The core application is entirely written in Scala and is present in this one simple Scala script file here. The application expects a parameter which provides it the absolute path for the configuration file, which includes details about connecting to Twitter and various other parameters that Flink would need, such as the elastic host name, elastic port, cluster, index, as well as whether logging is enabled and where these logs would be submitted to. Once all these parameters have been set, we obtain the streaming environment for the Flink engine, and we initiate the call to parse the tweets from there on. The define parse tweet function is a function that is written to basically parse each of the tweets for the time zone information and submitting the time zone and count back to the mapping function. Once the environment for the Flink engine has been obtained, the data source, which is Twitter source here, is assigned to a variable called tweets, and functions against the tweets variable are performed. These functions are very similar to our MapReduce functions, and we can see that we are processing a tumbling block based window operation and calculating the count. We will now run the code to show it working in live. We can see that once there are no more additional logs in the console, we can verify that the application is working by going on to verifying if the elastic source is able to obtain any data. Since we are using a window count of 10 seconds, we expect this count to increase every 10 seconds. And we can see that the number of records received in Elasticsearch has increased from 688 to 730 over the last 10 seconds. And we can see that we've accumulated a total of 82.7 MB during the course of this project. Prior to visualizing the data, it is important for us to package the source code into a jar file and execute it against the cluster. For this, we will go and stop our code and execute the packaged jar file. Once the job has been submitted to the Flink engine, we can see it is in running status. We can further verify the status of this job by going to Overview, and we can see that there are a total of only 3 slots available out of the 6, and there is already a running job which has been running for 16 seconds. We can see that it's a custom source, there is a map, filter, stage in the code, as well as a tumbling block. We can see that over the span of 26 seconds or 29 seconds, 4.4 MB has been received, and we can further verify that this data is being sent to Elasticsearch by querying the Elasticsearch engine. As can be seen, the number of records increased from 11391124 to 11391177 over a span of 10 seconds. And we can see that there's been no documents that have been deleted, as Elasticsearch and the application have been configured only for inserting records and no deletion. We can now move on to visualizing this data in Kibana. By going to the Discover tab of Kibana, we can visualize the data or the frames that are flowing into Elasticsearch as they come in. The following screenshot shows the amount of data that has been flowing ever since we started the application and the number of tweets counts that are coming through with each of the frames. We can further go into visualizing the data based on any of these visualization tools available. For this presentation, a dashboard was already made with predefined visualization. The current dashboard is displaying data for the 9th of May between 1937 and 1942. We can expand this window to include more than a week by simply changing the parameter here for the date count and allowing Kibana to show us all the Twitter counts that are available. We can see we've collected over 1.1 million tweets, and the average number of tweets per second is 4.4 3. Note that this is based on us having a tumbling block window of 10 seconds. This data can be configured to display in real time, and we can further tune the parameters to only display data relevant to the current day. The visualization to the left shows the top 5 time frames when the tweet count was the highest in our data stream, and within those top 5 frames, the zones which had the least number of tweets. We can see Seoul in this time frame on the 9th between 8:36 am 30 seconds and 8:40. The Seoul, Madrid, Kuala Lumpur had the least number of tweets. Whereas for this time frame, which was at 8:04 am on the 9th, Kuwait, Hawaii, and Brasilia each had only one tweet count. Please do note that the tweet samples we are receiving are a sample frame from Twitter and not the entire set of tweets that's passing through the Twitter framework. The intent of this project was to demonstrate the capabilities of Flink using a live streaming source. Flink is a true streaming platform as opposed to micro batch processing of Spark, which also supports batch processing. With its support for complex event processing, a machine learning API, graph processing, and its continuously growing API, the possibilities are endless. This could be the technology that soon replaces Spark. Thank you very much for going through my presentation. I would like to take a moment to give credit to all the following bloggers from whom I was inspired to conduct and complete my project. Thank you.